Okay, we've seen how to prove this theorem about the Laplace transform of a periodic function. And we've seen that we just started out here, we just write down the Laplace transform of the function, break it into two parts, one part from 0 to 2, the other part from 2 to infinity, and then you do a little bit of simple work with this integral, translate it, do a couple of other things, and the theorem pretty much falls into your hands. Well, we just saw that. Now I want to look at it geometrically. So let's just say that you have the graph of a function f of t, and it's periodic with period t. That is, here's the function from 0 to t, here it is from t to 2t, here it is from 2t to 3t. It's supposed to be the same every time. I drew something kind of bizarre there, and didn't get a really great copy, but I think you get the idea. It's supposed to be the same at every period. Okay, well, there's your f of t. Now let's say you're integrating f of t times e to the negative ts. Well, what does e to the negative ts look like? When t is 0, it's equal to 1. And I've just, without any real loss of generality, I've assumed that the maximum value of this function is always 1. Not necessary to do that, but it's easy to vertically stretch that function and see that you get the same argument. Okay, so I'm going to draw now an exponential function. Okay, there's a graph. It's supposed to represent the exponential function e to the negative ts. So there's your graph of e to the negative ts. If I multiply e to the negative ts by f of t, well, at this point f of t is 1, so that I'm going to multiply the value of f of t by 1. I'm going to get a point right there. Now it's going to be equal to the f of t function at this point. Now by the time we get out here, this has fallen maybe to half its value. So that by the time I'm out here, the function, and let's go ahead and let it move all the way over there, it's only going to be, okay, when we multiply f of t by e to the negative ts, it's only going to have half the y value. And then by the time we get out here, and of course this function, this period of the function is going to start out with a value about here. Okay, by the time we get out here, the value is going to be down to maybe a third to a fourth of the value. Now if it's half here, it's going to be a fourth here. And just go back to the properties of exponential functions to understand that. So here are some representative points. Another important representative point might be here, and I'm not going to go through the details. The value is going to be closer to the x-axis than it was here. We actually probably got it a little bit too high there. And here it's going to go a little closer. Well, what's going to happen then is you're going to end up with a graph of f of t times e to the negative ts. It stays pretty close to f of t up here, but now the e to the negative ts is starting to decrease a little bit, so it's going to come down a little bit below this graph. It's going to go through 0 at the same point. It's going to dip down here. It's going to come back up here and do this sort of thing. Then the next period is going to start here. It's going to have very similar behavior. Okay, it's going to rise up a little bit here. It's going to come down here. It's going to come down here. And it'll come back through 0 here. Probably go out to here. The next period is going to start out maybe here, go up here, And I could have done a better job of drawing this thing, but it's going to come down. It'll come down through here, come up here. Okay, well, what you're getting is multiplying this function by decreasing values of e to the negative ts, so it decreases progressively as you move on, then decreases here progressively, and so forth. Okay, if you then look at what we have, okay, we have the first period. Now, assuming we can integrate this function from 0 to t, then we've got the top part of the integral. This value here of the e to the negative ts function is going to be e to the negative ts evaluated at little t equals big T. So right here is e to the negative big T s. That's the value, the y value if you wish, of this function at this point. Okay? Now I'm not going to go through the detailed argument, although it wouldn't be hard to make. If I pull this blue graph back to here, then it's going to look like this. This period comes back to here. This period comes back to here. And then the next period will be even smaller. Okay. Now, this graph is then the graph of e to the negative capital Ts f of t. Yep. Okay. Again, not going to try to completely make that argument. So, the blue graph, and I've kind of messed up my picture here, smudging it with my fingers as I attempted to sketch the graph, but anyhow, the blue graph is the graph of e to the negative little ts f of t. I left something out here. The graph I have here is shrunk by a factor e to the negative ts. Okay, because everything that happens from here on is e to the negative capital Ts times what happened to the original function. So we have e to the capital Ts, e to the negative little ts f of t. Okay, constructing these graphs, then we see that the integral from 0 to infinity of the blue function, this function, is going to equal the integral from 0 to capital T of this function minus, plus everything that happens from here on to the blue function. Well, everything that happens to the blue function from here on to infinity is what happens to the orange function from 0 to infinity. So I can say that, uh-oh, almost lost my chalk. Okay. I can say that the integral having trouble making a good infinity down there. From 0 to infinity of e to the negative ts f of t dt equals the integral from 0 to capital T of e to the negative ts f of t dt. That is, the integral of this blue function forever is equal to the integral of the blue function just from 0 to t plus its integral from t, capital T, to infinity. And that integral from capital T to infinity is just the same as the integral of e to the negative ts, capital Ts, this orange function. Okay, I don't have to read it to you. So I can say that's plus e to the negative capital Ts times the integral from 0 to infinity of this. And if you remember what happened in the proof, of course, or I can just say it right now, this integral is the Laplace transform of f of t. Multiply it by e to the negative ts. This is the Laplace transform. So what I have is the Laplace transform equals the integral over the first period times e to the negative ts times the Laplace transform. That can be rearranged to give you this. Again, that's the geometry, the picture of the function. That's an attempt at the picture of the function, and I think it's important to kind of understand that.